lessons, online lessons. So today we'll be dealing with a very sensitive but easy topic. Not necessarily easy, but yeah, it's understandable. I'm pretty much sure you will understand once I'm done here. Okay. There are not many calculations in this chapter, so you should get it. It's more like electricity in disguise. So okay, let's get to it now. Okay, the chapter that we're going to deal with is a famous chapter that is called Electrodynamic or Dynamics, right? Now, electrodynamics, you wonder why I put these things here, right? Electrodynamics, you studied it in grade 11, where you spoke about Faraday's law, right? About how electricity is induced, right? Basically, it's all about the induction of electricity or electrical induction. Right. So now what happens with electrical induction is that we have two types of whatnot. As we were studying in grade 11, we realized that we have different types of conductors. The first one, we have an electric motor, right? An electric motor. And we also have a generator, right? So now with electric motors, we when we spoke about this, we said they convert electrical energy to mechanical energy. So with electric motors, you convert electrical to mechanical, right? Now with generators, you convert mechanical to electrical. So now how do we do that? In this electrodynamic, we're not gonna focus more on this electrical motor, but we'll focus on generators, right? So now that's good. Remember that when we first spoke about Faraday in grade 11, the first law that we spoke about is this one here. It's Faraday's law. Then stated mathematically says the electromotive force is equal to negative the number of turns into the change in what? Magnetic flux. This is the magnetic flux, right? Being the magnetic flux, then this is going to be your change in time, right? So we said N represents the number of turns, and this represents the change in magnetic flux, then this represents the change in time. Then we also said the magnetic flux can be calculated using what? The magnetic field and the area, depending on a specific angle between A and B. So now I want us we get to understand how these two laws operate before we can get into it, right? So let me try to check something here. I think I have it somewhere here that is basically easy to, okay, here it is. So in grade 11 we also spoke about the right hand rule, the Fleming's right hand rule, right? So with the right hand rule, we said the thumb, right, which is this part here. Let me try to enlarge this picture so you can see properly. Yes. No. Let's move it this way. No. Okay, now it doesn't want to move, so it's fine. So according to Fleming's right hand and left hand principles, that the thumb tells us the direction of the current, right? So now the inside the palm, it tells us the force, the direction of the force. Now the fingers here, they tell us the direction of the magnetic field, right? The direction of those. So now what can we say? Now if you put your hand like this, always wherever the finger is facing, it's going to be your current, right? So this will tell us the direction of your magnetic field or your whatnot, right? So this is going to be your force, right? So that is how right hand Fleming's principle works. Some they define it in terms of when you have pinched your fist, right? So when you hold it upright, right? Now I think this is a better way of putting it, but you can still use the theory using the whatnot, the pinched fist, right? So now that's not what we are going to deal with. I want us to get directly into topic. So what we spoke about is just this part here, that it's possible that if you have a north pole and a south pole here, and you have a coil here, you can be able to conduct electricity, right? So now this is where we start to speak about AC generators, right? Alternating current generators. We have the direct current, we have the alternating current generators. These are the type of generators: the alternating current generator and the DC generator. So now all of these, they use these things here. This is what I'm going to talk about here. So we have the north pole, we have the south pole. So basically, if you have a coil here and you have bars of magnets with different poles that are almost near this coil, and you rotate this coil, you can conduct electricity, right? That is where we speak of the electrical induction, right? So now you can induce electricity. So electrical induction basically is when electricity is generated using a material that is next to bars of a magnet. So now we have different components on this system that is here, right? So now this is this one here, I'd say represents the DC generator. One of the reason is because it has the split ring. So when it has the split ring, the current will flow directly, right? So but I don't want to commit too much into that. We will speak about that in a bit. So if you look at this is a direct current motor or generator. So this one, it was identified by Michael Faraday, right, and Joseph Henry. Now the electric motor of a current carrying coil rotates in a magnetic field due to the magnetic fields that are here, because this coil will have its own electric fields, right? Electric field, a bit of electricity, right? Now this has magnetic fields, right? So now this coil will rotate due to the friction in forces between the electric and the magnetic fields. So now, how do we know that this is a DC generator? This one here. We know it's a DC because it has these two split rings here. The rings that are here, they are split. The rings that are here, they are split. Now, if they are closed like this one, we know that this represents an alternating current, or rather generator. Still same model, but just different apparatus. Still same direction. No, not really. Not the same direction. With the alternating current, the direction will move anti-clockwise, or the current will move anti-clockwise, right? Why is that? Because with direct current, the current is too much. So now it will move from anti-clockwise, and also the split rings, they also play a role in doing that. So with this one, the alternating current, then the direction of this will move clockwise, right? It will move clockwise. So which means that if you have a coil like this one here, and you have your magnet, right, and you have your slip rings, these are called the slip ring. These ones are called slip rings, right? The reason why they are called rings is slip rings is because they do not have any opening in between them, right? So now this is a coil, this is above a magnet, this is a slip ring, right? So when it conducts electricity, the electricity does not get cut in between the rings. It just flows just like that. Whereas this one, electricity get cut off sometimes. So now there is a reason why we use AC current and not direct current. I'll tell you later on during the lesson. Now I just want you to understand this theory part here. So you will have a bit of powering these two things, right? So we have motors. Motors, they convert electrical energy to mechanical energy. Now, uses the first thing, electric lifts, cars, etc. So according to Michael Faraday, or in Michael Faraday's law, the induced electromotive force, or the EMF, in any enclosed circuit is equal to the time rate at which of change of the magnetic flux through the circuit, right? So now current can only be induced only in an enclosed circuit, all right? Okay, electromotive force is equal to negative the number of turns, right, multiplied by your magnetic flux, the change in magnetic flux over your change in time, right? So basically that is what they're saying, the rate at which the change in magnetic flux through the circuit, right? So Lenz's law states that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop, right? So that's basically that. So this is how you can determine your direction. So now if this is your magnetic field and you have your loop here, you have your magnetic field lines here, right? So now you have this one here, which is going to, we pretend that it's your slip ring. This is how we can determine the direction of this whatnot. If you put your right finger up like this, right, and you bend your fingers a little bit, right, then the first thing that you will see is the induced the direction that of the many fingers that you have bent there will be your induced magnetic field lines, right, which is going to be this one, right? Approximately, we can just call it the induced current, right? So that is how we can tell, we can define this, right? So we also have what we call the normal, right? Then we have the magnetic magnetic field, right? And here you have the surface area. The reason why we say that this equation qualifies is because of this thing that you see here. So now, if this becomes your area and this becomes your magnetic field, right? What do we say? We say what? Your magnetic flux will be equal to your magnetic field times the area cos of theta. This is rightfully so, because if you look at this, we took this to be what? Let's take this to be your magnetic field, right? Because we have a surface area here. So we can say what? Rather magnetic flux there. Cos theta is going to be equal to the magnetic flux over BA, right? So your magnetic flux is going to be your BA cos of theta. So cos of this angle that is here is going to be directly proportional to this and inversely proportional to this part here. So that's basically how we can put it. So Faraday's law stated mathematically is like this, right? Now, AC generator. What is AC generator? The following diagrams show the variation in the positions of the rotating loop in the EMF that is induced, right? Now the AC generator. Okay, this represents the let's say this represents the area, the magnetic field. So how are we going to go about business of the day? This is how, using Fleng's right-hand principle. So basically, if you put your thumb to face downward, right, and your fingers not downward, no, but if you face the towards the screen, right, and you place your fingers, you open them wide, you will have your force that is going up, your current which is going sideways. There's force that is going up, current that is going this way, then you have this magnetic field here, right? So now with AC, as we know, this represents the bars of magnet. This is how we can see that this is AC. Then we have your coil that is flipping around clockwise, right? And we also have these things here, we call them the slip rings here. Now this is how we can identify that. Also, as the loop is rotated from the position 1, right, then the angle there is equal to 0 degrees. So to 2, it's going to be what? This is 1, right? If we rotate it to this format, it's 1. It means the angle is 0. Now if we rotate it to 2, then the angle is what? It's 90 degrees, right? So if we rotate it again to what? To 4 or to 3, it's going to be what? It's going to be 180 degrees. So we're moving clockwise, in a sense that this one here is going to be 0, 90, and this is going to be 180. This is going to be your 270. So now that is how we can deal with this, we can attempt this. So this is 0, this is 90 here, this is what? 180, this is 270, right? Now the flux is negative. Remember that cos of 180 is going to be whatnot. So cos of 90 here is going to be 0, right? For this one here is going to be what? Cos of 0, I think it's 1. If we can look at it, let me try to verify that. All right. Cos of 0 has to give us 1. Exactly. Cos of 0 gives us 1. So we have what? 1, 0, 1. Negative 1. 1, 0, negative 1. And this is presumably going to be 1. So now, let's continue with that. So this is how we can deal with the whole trajectory of the thingy, the AC, in terms of rotation. So now at the 4, as we spoke, it's 270, right, to 1. Then the angle there is 360. Now flux is positive and increasing. So the moment it moves from this point to this point to this point to this point, this is 270, and it passes to this point here, the flux is positive, right? B is positive, and is what? Is increasing. So now, before we get to DC generators, right, I want you to get the direction very well. This is the upward one. This is 1, right? This is 1. This is going to be your 0. This is going to be your 90. This is going to be your 80. And this is going to be your what? Your 270. Not that it's going to matter in exam, because presumably you're going to get something that is straightforward. But you need to know the direction. So now, let's talk about DC generator. DC generator, okay, an AC generator has this kind of thing, graph, right? The current is fluctuating, right? As with the direct generator, the graph is only on the positive side, so it goes down, upward, down, down. There's no negative value there. So now this is how we can identify that this is a DC, due to this slip. Those we said is the slip. This one is the split ring. They are split in between. Also, they have what we call bars of magnets here. We have bars of magnets. Then you have your coil here, right? And this is going to be your whatnot, your cell of some sort. So now, similar to AC, except the contacts of the to the rotating loop are made by the split ring or commutator. Now here the output voltage always has the same polarity, and the current is pulsating during this current, right? So now the contacts to the split ring reverse their role every half cycle. That is why we have this kind of graph here. Now the same time, the polarity is of the induced EMF reverses, and hence the polarity of the split ring, which is in the same as the output voltage, remains the same. So now this is in terms of torque, but I don't want us to talk in terms of torque. Never mind torque, because you're gonna do it in your first year. So I'm gonna scrub this, and I'm gonna scrub this formula here, so you won't take it, it won't affect us here. So now we're left with this. The force is equal to your current, the length of the loop, your magnetic flux, sine of theta. The angle is also necessary. We're still going to use the same right hand rule, right, to calculate, and we're still going to use the same 1, 2, 3, 4, knowing that this is 90, this is 0, this is 90, right? This is 180, and this is 270, and this is 360 here. So now, according to our DC, we can say that the force is equal to your current multiplied by the length of the loop, right? Then multiplied by your magnetic flux sine of theta. So now the angles will vary, right? In a sense that when you put sine of 0, you're no longer going to get 1, but you're going to get 0. So it means when you put sine of 90, you're bound to get 1, right? And when you put 180, you're not going to get the negative 1 here. You're going to get 0. So when you put 270, you're going to get negative 1. Then 360, you're going to get 0. So now the whole chain changes when it comes to this. So the rotation can either reach 1 at this point, right? So that's what we need to bear in mind. Now the DC are responsible for what we call the electric motors, or what we have in our cars, right? The electric motors are connected, or are DC connectors. So now this is how they generate electricity. They use the power, they have the magnetic field around those. So those magnetic field, as they rotate, right, clockwise like that, then they induce current, but the current does not remain in the same, does not become negative. It remains in the same segment, right? Which means it's going to most likely be like this, right? So that is basically that. Now the basic knowledge is that the magnetic fields and the electric field, these two things are not the same. The magnetic fields, these are field lines around both a magnet. The electric field, these are fields that are experienced in and around the substance that conducts electricity. Now, the sources, magnetic fields, the sources of magnetic fields, the sources of magnetic fields are your magnets and your electric current. So now your electric field is as a result of your electric charges. Now the uses of AC, the first thing we need to think about is generator, right? So the main generators in nearly all electric power plants are what? AC. They are alternating, right? So now this is because of the simple electromagnetic device called the transfer that makes it easy to increase or decrease the voltage of the alternating current. Almost all household appliances utilizes AC. This is very important, right? We use it at our homes, right? It's used to generate electricity. Even in our appliances, almost every one of them has got AC, right? So now the uses of DC generators, factorizes that do not that do electroplating, right? And those that produce aluminum, chlorine and whatnot, industrial materials, use direct current and use DC generators. So do locomotives and ships driven by the what? Diesel electric motors? Because commutators are complex and costly, many DC generators are being replaced by AC generator combined with electric rectifiers, right? We'll deal with that later. Now we're going to leave this equation out. I'll tell you why later. What we need to be aware of or familiar with is this formula that is here, that we call the VRMS, then which is equals to what? Vmax over the root of 2, right? And also the I RMS, which is equals to the I max over the root of 2. This is the two formulas that you need to know, right? And also notice that your PRMS is going to be equal to your I RMS VRMS. These are just your simple electrical equation. They just changed into RMS. So now your VRMS is equal to 1 over the root of that. If you are given this voltage here, which is going to be your maximum supply, right, you can find the RMS of this. So to find the RMS of this, you can say VRMS over the root of 2. Then you can say 220 over the root of 2. Then you get this voltage that is here, 155.56 volts. So that is basically what I wanted us to talk about. So now that you have the VRMS, you can try to work around into solving this further, right, into finding your I RMS and your P RMS. I will deal with more with calculations on the next video. I just wanted us to go through the theory. So this graph here is your AC graph, right? This here is your AC graph. So now the moment you see this kind of graph in your examination, what is it? You should know that it is what? It is your direct current graph, right? That is that for now, till we speak to each other later. This is what I wanted, or what I had for you to do. Right.